All right. Good afternoon, everybody. How is everyone doing today? Today we are continuing our triangle study, finishing actually, wrapping up. This is the final triangle piece of the triangular puzzle. Do they make triangular jigsaw puzzles? I'll have to look into that. Anyways, we're going to expand from yesterday with the inequalities, sort of, so a comparison, as it were. But instead of within a single triangle, we're now going to compare one triangle to another. All right? But before we go there, let's review answers from yesterday. So go ahead and open up yesterday's worksheet. Take a look at your work and compare your answers to mine. One and two, pretty straightforward. Yes and no, making a triangle. 3, you needed the range of possible triangles. So what's the biggest possible third side I could have and the smallest possible third side from these? And to get this, you're going to have to add and subtract the two known sides. So think of it as, if these are the two smaller ones, the larger one is not allowed to be bigger than the sum of those two. Clearly, you just add them together and get the 53. But if it's smaller, then that leaves the 36 to be the large side. So I need something plus 17 is equal to or more than 36. So we take 36 minus 17 to get that smallest possible side. Okay. 4 and 5, put the sides in order within the triangle. Pretty straightforward. Number 6 was a little bit more involved as it had overlapping triangles. So you had to compare, okay, this triangle, B versus C, and then this triangle, let me compare C and D, that kind of thing. There. 7 and 8 kind of led you to a new secret hidden feature of triangles, as it were. But both very doable. So I'm going to go ahead and call this angle alpha here. It was otherwise unlabeled, just for ease of reference. So we know from the triangle sum conjecture that these three should add to 180. And we know because they form a linear pair that A and 142 should add to 180. So if both those sets add to 180, I can set the groups equal to each other, and then they share that alpha in common. So I could subtract that from both sides. You imagine writing out an algebraic equation, which leaves us with this exterior angle 142 is equal to those non-adjacent interior angles of the triangle. And we've shortened that together and called it the exterior angle conjecture. But it's just a short way of piecing this guy equal to those two, and so you can subtract and get 76. Same with this one to find 79, except you know it's isosceles, so these have to be the same. Number 9 was pretty fun. I know linear pair tells me that this guy has to be 120 from 180, leave 60. This has to be a linear pair, so 180 minus 160 is 20 here. So now I've got 60 and 20, but this is 90. 60 plus 20 plus 90 is not 180 degrees. No, so it doesn't form an actual triangle, or one of these had to be wrong. There, right? Very strange business there. Right, and number 10, kind of playing off of 7 and 8. Again, you could use the exterior angle conjecture as just a shortcut for linear pair and triangle sum fitted together. But it tells me that this angle PQS, so this guy here, plus the x is going to have to be equal to this 2x out here. which means I can subtract the x off of both sides. I get angle PQS has to be equal to x. So now I have these two angles are equal to each other, which means it must be isosceles because, well, we have a thing called the isosceles triangle conjecture, and that's just a shortcut for saying if a triangle is isosceles, then the base angles are congruent. So I want to take the converse of that. If the base angles are congruent, then it's isosceles. Work backwards. So your explanation might have more words. The usefulness of these conjectures really comes down to a shortcut phrase that you can insert as part of your explanations. Any questions then on that page? No? All right, then let's go on to today's topic, which is similar triangles. We're going to compare two triangles to each other, and they're not exactly the same, but they are similar. What does similar mean? Similar gives us the same shape, but of a different size. So this is literally what happens when I draw something on here and scale it up bigger or smaller. I haven't changed the shape itself, but I've made it bigger or smaller. I've scaled, zoomed in or zoom out, right? Just changed its size there. Okay? Compare that to congruent. A congruent set of shapes are the exact same shape and the same size. So I cannot scale them around at all. Now, this means for similar triangles specifically, you will have a set of corresponding angles that are congruent, and the corresponding sides are proportional. So they're not the same length, but the relationship between the lengths are the same. If you were to compare one side to another, and then another pair of corresponding sides, you would get the same relationship between them, right? So you could say here to here, so one side of the triangle to the other side, and in the other triangle we have one side and its other side. So that has the same relationship, in this case, times 2. Right? This is a proportion. It's an equation of two ratios, two equal ratios, or fractions are just a type of ratio. But what's also neat here is that you can go horizontally and look at it this way. Say, hey, both times in the numerator I'm multiplying by 3, and in the denominator I'm multiplying by 3. So if this is two sides in our triangle, this is two sides in the other triangle, I've got the same relationship from one triangle to the other. It's saying this triangle is 3 times bigger than this triangle, as exemplified by the two sides given. And that will be true of all 3 sides. You could pick any combination thereof and set up a proportion here. So we've had tools for finding the third side given 2 other pieces of information in the triangle. Now we can find a third side given only 1 piece of information from a triangle, as long as we have a different similar triangle. Take a look at this example. All right? Now, follow along closely, because in a moment after this, I'm going to ask you to do one for yourself. Okay? Your participation today is required. So I have triangle ABC, squiggle triangle XYZ. What the heck does that mean? Well, remember our congruence symbol was equals with a little squiggle on top? So this is our symbol for similar. Just a single squiggle, tilde, right? To mean similar. So they're the same shape but different sizes. And the correspondence comes in the order of the letters. That's why it's so important to put these names in the right order. A corresponds with X, B corresponds with Y, C corresponds with Z. Which means I can see the only given length in XYZ here is the 19.5. That has to correspond with the side 13 there. So if I wanted to find Z, I could set up a proportion here and say Z corresponds to 5. And since I did large triangle over small triangle, I've got to repeat that on the other side of my equation. Large triangle measurement, I have 19.5 over the corresponding small triangles, 13. And now I have an algebra equation. I can just solve for Z. So multiply both sides by 5. The ones on the left cancel out. On the right-hand side, I have 19.5 divided by 13, which is, real quick, do the math, by which I mean remember it from last time. And that was 1.5 times 5. Half of 5 is 2.5, so plus 5 again, 7.5. Any questions on how I got that? Okay. Along the way, we can see this from the two known values, this comparison of large to small gives me my scale factor here of the triangles, which is just a fancy term for how much bigger, how many times larger is the big one to the small one. It's 1.5 times bigger, been scaled by 150%. And similarly, we set up a ratio for y. And I'm going to do it a little bit differently this time, just so you have an example of both ways. You could set large over small, so the corresponding sides on top of each other. Or I can put two sides of the triangle in one ratio. I could do y over 19.5. And in that case, I did the middle length over the long side. So for the small one, I need to do middle length over the large side. So make sure you put them in the same order. And once again, I've got a basic equation. I can just multiply by 19.5 on both sides. Or, notice, my scale factor from 13 to 19.5 is times 1.5. So to go from 12 to y, I need to do the same thing, multiply by 1.5. So 12 times 1.5, half of 12 is 6, 6 plus 12 is 18. Any questions on how I did it that way? No? All right. So here is your challenge then. You are going to apply this concept of similar triangles in with casting of shadows. Very common scenario when you want to know just how tall this tree is over there, but you don't bring your ladder with you. All you have is a simple measuring tape, and it'd be really impractical to try to like climb up here and get to the very tip top of the branches where they're weak. They'll snap, I'll fall. I don't want to risk it. We're going to stay on the ground. So the sun is shining, casting a shadow on the ground. I can measure how long the tree's shadow is. I can measure how long my shadow is. And I know how tall I am. Use that to set up similar triangles. So here we have the height of the tree, your height. Your shadow's length here is 7. You are 10 feet from the tree, so altogether the tree's shadow would be 17 feet. These are all feet. What is the height of the tree? Go ahead, set up the proportion, and send me your answer in chat. I'm trying to make an apostrophe. There. Alright, you've had 3 minutes anytime now. Oh, I stand corrected. 4 minutes. What do we got? How tall is that tree? Seven. I'm afraid it's a little more than 7. 7 is the length of your shadow here. Ooh, Vanessa's got an answer. Very good. And yes, Vanessa, that is correct. And no, not 10. 10 would be too easy, Leslie. That would say that the tree is twice as tall as you are, but its shadow length is not twice as long as your shadow. Right? Double of 7 would be 14. Its shadow is longer than 14, so we're looking at something at least more than 10. Start with setting up the proportion. I always like to start with the variable I'm trying to find. In this case, h. Set that over top of something. I like going within a triangle. So if this is this side of the triangle, let's pick the other side from the same triangle. So I'm going to put it over 17. Set that to the ratio of sides in the smaller triangle. So we did the vertical over horizontal, so do vertical over horizontal again. 5 over 7, solve that for h. Yasmin, did you round? Is there more decimal places to that? Pretty sure there should be more decimal places. I didn't specify what to round to, but if you ever end up with a decimal answer, unless it explicitly told you, don't round it off to an integer. Don't make it look like it came out a perfect integer when it definitely did not. At least include one decimal place. 3 is a good rule of thumb. Any more answers? Yeah, all right. Well, if you do get one, go ahead and take note. You should end up with something around 12.14. feet there. All right, so keep that in mind. Now, for the rest of the period, go ahead and start on the worksheets exercises with similar triangles. Most of these are fairly straightforward, although number 4 kind of has this stacked triangle effect, like we had with the tree, where you had the one triangle on top of another. So make sure you're adding things together appropriately there. Same with triangle here for 5 and 6. 7 and 9 are both doable, but 8, however, relies on some properties of circles, and we haven't gotten to circles yet. We come to that next week. So go ahead and skip number 8 for now, unless you're really curious and you want to look it up in the big fat notebook and see if you can find out how it works. But otherwise, you're pressed on time. Skip number 8. All right. And with that, unless there's any final questions, I will leave you with the rest of the class time.